Hey, and welcome to a video on my EMCO CNC mini lathe. Today I will show you the process I went through to resolve problems that I had with the Z-axis. The Z-axis was not running very smoothly and on one occasion even got stuck. I ended up taking the lathe apart to look for the root cause and even managed to mostly fix the issue and put it back together. I've been using my small EMCO 50 CNC mini lathe for a couple of years now, mainly for making small parts out of brass and plastics. Although I am quite happy with the accuracy and surface finish of parts made on this lathe, there have been some issues. Sometimes the Z-axis seems to have quite a bit of resistance to the point where I can still hear the stepper motors trying to get into position after a move should have been completed. It did not affect part quality much, but it still seemed like this axis needed some maintenance. After removing the Z-axis motor, I was able to manually rotate the ball screw and noticed that there was indeed quite a bit of resistance. It was hard to get it moving after a complete stop, which would indicate some kind of stick-slip effect. However, even when the ball screw was already rotating, it still felt like there was too much resistance. To investigate the issue further, I decided to have a closer look at the ball screw and ball nut. If you want to get access to these parts on an EMCO 50 lathe, some other components need to be removed. I will speed up the video for the disassembly process. I removed the tool turret, tailstock, chuck, and part of the housing, so I could access screws that would allow me to remove the lathe bed. On the side of the lathe I had to remove the spindle encoder and take off the drive belts. Also, the cover plate behind the bed needed to be removed. Here the stepper motor for the X-axis is removed. I could have left this on, but that would mean I would have its wires in the way while working on the lead screw. Finally, I was able to unscrew the lathe bed from the enclosure. There are two screws on the side of the enclosure, which are screwed into the headstock. I'm removing these first. Now there were only two large screws that needed to be removed before I could take out the entire lathe bed. Having the lathe on my workbench makes it a lot easier to have a look at the lead screw from all sides. It was not strictly necessary, but I also removed the pulleys from the backside of the spindle. The first thing I did after that was to clean the bed and remove any oil and chips, so I would not have them falling onto the workbench every time I moved the machine bed. At this point I thought it was probably a good idea to start wearing gloves. I used some disposable wipes for cleaning. I did not clean the bare metal parts, or when I did, I applied some oil on them after cleaning to protect them against rust. The cross slide assembly has an interesting design. The slide travels with metal-to-metal contact on the top slide. This is regularly lubricated with Way Oil 68 to keep it running as smooth as possible. However, on the bottom side there are plastic gibs, which are used to constrain the slide from the opposite side. From what I understand, these plastic gibs were mounted as standard from the factory. If you have an EMCO and you know whether or not these are the original ones, please let me know in the comments. These plastic gibs might be one of the sources for increased friction, but at this time I'm not replacing them. I have seen people replace them with Igladur material from iGUS, but for me this material is not easy to get hold of. I wanted to see if working on the lead screw alone would solve the problem, so I decided to keep the existing gibs for now. After unscrewing the gibs, the whole slide assembly can be removed. The slide also appears to have a non-even wear pattern. Also here I'm not sure how large the contribution of this is to the overall issue, but this might also be something worth looking into at some point in the future. only slide by hand, and without the bottom gibs in place, there was very little friction. This is nice, but of course not representative of actual use, when there are gibs, a tool changer and a slanted bed in play. But by itself it seems okay. The block holding the ball screw nut was now also exposed, so I could get a feeling of how well the bearing performed in terms of resistance. Manually I could feel a lot of resistance, and it was also not always consistent over the length of the ball screw. Some of it can be expected because of the preload on the bearing, but it was much more than I felt on the other axis. On the side of the block there is a grease nipple. Since I have had the lathe, I have not been able to use this as it appeared to be clogged. This left me with the only option to lubricate the lead screw outside the bearing block, which is not ideal. Normally you would press grease into the bearing, which would force out older contaminated grease. If you are only lubricating the lead screw like I did, this does not happen. Behind the grease nipple there is a channel that should lead grease into the ball nut. To isolate the problem for lubrication to the grease nipple, I removed the set screw in the middle of the channel and injected some grease here. It did work its way through the ball nut onto the lead screw. This confirmed that the grease nipple was at fault here. I also tried to flush the ball nut with some light oil, but this did not make it run more smoothly. At this point there was no other option than to remove the ball nut. It is retained in the bearing block with a ring that can be loosened with a wrench. On the side there is also a set screw that needs to be removed before the ball nut can be taken out of its housing. This close-up shows the slot for the set screw and a round hole for lubrication of the bearing. I noticed that there were some chips trapped inside the bearing housing, and also the grease was full of dirt and chips. I cleaned everything as best as I could and tried again. Still a lot of resistance. Here I tried to flush the ball nut again, this time with grease instead of light oil. There was clean grease coming out of the sides, but still the issue remained. This meant that there was no getting around it. The ball nut had to be removed. I was a bit scared of doing this, as this was the point of no return. I had seen people replace balls on a ball nut before, but this part is really tiny. The balls themselves are only 1.5 millimeters in diameter, or 0.06 inches. I also inspected the bearings on each side of the lead screw. On the left side there is a floating bearing. It was in relatively good shape, but I could feel that it was not running like a new bearing. This would be easy to replace, and I had to remove it anyway. I will show this later in the video when I put things back together. On the other side there are two bearings. These are fixed in place by a ring, which was pressed into place by deforming parts of the bearing block. This is not something that I would be able to disassemble easily. Since these bearings were also relatively okay, I decided to leave them where they were for now. As you may have noticed, there are several parts in need of attention here, but I also wanted to make sure that I would not end up in a situation where the lathe would be out of commission for a long time because I was doing a full rebuild. Anyway, back to the other side of the lead screw. I don't have the right pliers for removing a small lock ring, but with a bit of patience I was able to remove it using a screwdriver and small pair of pliers. Pro tip: if you like a bit of a challenge, nothing beats using the wrong tool for the job. Yes. I manually moved the ball nut to the end of the ball screw. Because it was full of grease and the balls are very light, they nicely remained in place after removal. What I could have done is buy a new ball nut, but these are very expensive at around 300 euros. So at first I wanted to see if I was able to replace the balls and if that would help. It just seemed like too good of a challenge to pass up. I used an ultrasonic cleaner to get all the balls out and clean the inside of the ball nut housing. The clean performance is improved by raising the temperature with the built-in heater and by adding an appropriate cleaning solution. I'm using Ticopor R33. This is a general cleaning solution for greasy parts. After about 15 minutes in the ultrasonic cleaner, the balls were clean and separated from the ball nut. I counted 51 balls, but I'm not sure if this is the original number for this type of bearing. Under the microscope, I was able to inspect the condition of the balls. 3 of them showed severe damage. Parts of the outer layer had been completely broken off. Seeing this, I was not really surprised anymore that the ball nut was not running as smoothly as it should. From AliExpress, I ordered the same size of bearing balls as the original size, which is 1.588 millimeters or 0.0625 inch. Both the old and the new balls measured a bit lower, between 1.581 and 1.586. I'm not sure if I can trust my measurement setup or micrometer. At least the new bearing balls had the same size with this measurement method as the old ones, and this gave me enough confidence to use them. Now onto the hard part, getting the balls into the ball nut. First I cleaned the ball nut and removed the plastic parts on each side. These are actually 2 parts, an outer ring which acts as a seal against dust and debris, as well as an inner ring, which also has a guide to get the balls into the recirculating channel when the bearing is rotating. The inner ring was hard to remove as the material is very stiff and not easy to pull out, as it does not have any features that you can easily grab onto. In the end I did manage with a pair of pliers that are actually as small as a pair of tweezers. As you may know, during the rotation of the ball screw, the balls circulate through the channel between the screw and the ball nut. When they reach the end of the nut, they are recirculated to the beginning of the nut through a return channel. This is the hole that you can see here on the side of the ball nut. It still had some bearing balls inside that are removed with a picking tool. There were also still some balls in this guide ring. I'm not sure what the ring is supposed to look like, but I think it still has the original shape for scooping up the balls out of the lead screw. Regardless, I do not have a replacement part for this, so I will have to reuse it and hope for the best. After cleaning the ball nut again in the ultrasonic cleaner, all of its features become visible. Here you can clearly see the grooves in which the balls are guided around the ball screw. On the side we have a lubrication hole, as well as the slot for the set screw that holds the bearing nut in place. I started filling up the return channel with bearing balls. As you can see here, I am using the grease to pick up the balls and drop them into place. Also, for placing the balls back into the tracks, I used some grease to pick up the balls and place them in the correct location. I'm using a picking tool that is angled at 90 degrees. This makes it easy to get balls into the ball nut while still being able to see what you're doing. This is a job that requires patience and perseverance, but I noticed when I got the hang of it, it became easier. I lined up the balls back to back in the grooves as best as I could until all of the grooves were completely filled. From what I understand, it is not an issue if there is still some room left, or even if you miss a couple of balls. After the ball nut was completely filled, I placed back the covers and mounted it back onto the lead screw. The diameter on the machined end of the lead screw is large enough that it does not allow the balls to escape through the gap when screwing the nut onto the lead screw. This makes this process surprisingly easy. For larger lead screws, you would have to insert a bushing into the nut and then slide it onto the machined end. But that is not the case here. I actually removed it and screwed it back on to make sure that all the balls stayed in place, which they did. The other thing I wanted to address was the grease nipple. After running the block through the ultrasonic bath, I did one last test to see if I could keep the original grease nipple. Some grease reached the bearing, but since it took too much pressure to get a bit of grease all the way to the end, it was probably best to replace it. I carefully drilled out the old part with a drill bit that was just undersized to the hole. From a local supplier, I was able to buy some new grease nibbles with the correct size. These are the type that you are supposed to press in. As a backup, I also got some of these screw-in type, but I ended up not needing them. This is the type that I used to replace the old part. To protect the grease nipple from damage, I also used a piece of Delrin as a punch. Since I was shopping online, I also bought a smaller type grease gun instead of the larger one that I've been using until now. This one is much smaller and it can be operated with one hand instead of three. This type can simply be filled from the back and it is ready for use. So it was time to put everything back together. First, the bearing housing was put into place and the set screw was screwed in but not tightened yet. After this, I mounted the retaining nut and tightened the set screw. It is hard to show on video, but the ball nut is rotating much smoother now. It still has some resistance, but this could be due to the preload in the bearing from the oversized balls. At least I hope so. The floating bearing on the ball screw is of the 626 type. These have a bore of 6 mm, an outside diameter of 19 and a width of 6 mm. From a local supplier I ordered two different types, which would be a candidate for replacement. The ones with the 2RSH suffix have a rubber shield on both sides, while the 2Z bearings have a metal shield on both sides. The metal shield of the 2Z type is less effective against contaminants like dust and moisture, but they should suffice for this application. The rubber bearings have a slight friction when rotating, and since this is the floating side, I wanted the bearing to have as little friction as possible, so I went for the metal shielded type. I might be overly cautious here though. If you have any tips on bearing shield selection for CNC machines, please let me know in the comments. Again, with a bit of fiddling around, I was able to place the retaining clip. Here I am mounting the support unit on the other side of the lead screw. The pulley can be secured by holding it with the appropriate pliers while tightening the set screw in the center of the pulley. With that in place, I was ready to mount the lead screw back onto the lathe bed. I tightened the screws on the end of the lead screw, but this was only temporarily, since the lead screw had to be aligned with the cross slide assembly to avoid any unnecessary strain on the lead screw. Mounting the cross slide assembly was done with the help of some wooden blocks as a riser in the center of the bed. Here I am screwing the gibs back into place. With that done, I was able to tighten the screws in the support units with the carriage as close as possible to make sure it was aligned with the lead screw. Also here, if you see any issues and have any tips on how to do things differently, please let me know in the comment section. The last time I worked on the lathe, I removed the optical encoder plate. I just realized that this actually removes about 1 millimeter of compression from the preload spring at the back of the spindle. Although I did not have any issues with the lathe since then, I wanted to bring the compression back to its original state. When you mount the bushing around the spindle pulley backwards, it actually extends somewhat and should be able to compensate for most of the length lost by removing the encoder wheel. This was also a nice quick fix. With the help of 2 clamps, I was able to keep the spindle bearings pressed into the headstock. This way I could easily mount the pulley and retaining ring. This is the first dry run. The Z-axis seems to be running okay. With everything back together, I did some test runs with the lathe off camera and the Z-axis does feel like it's running better now. It is difficult to quantify how much better, but when I rotated the lead screw manually, I did feel less resistance and it was also more consistent. What I did notice is that the resistance became higher when the turret was mounted. The weight of the turret hanging off the side adds some friction. It is also what I've read in forums, so it's not specific to my lathe. In my case, the uneven wear of the cross slide probably doesn't help, however. Well, for now that's it. Given the fact that I was able to fix the grease nipple and replace the broken balls, I feel a lot more comfortable in using this lathe. As you will have noticed, I am not a professional machine builder, so if you have some tips, please share them in the comments below. If you have made it this far into the video, I would like to thank you for your attention and please leave a like or subscribe if you haven't done so already. Thanks for watching.